Okay, hello everyone. Well, welcome to another working session in our efforts on the Wolfram Physics Project. These are very scary for me in some ways because we're working on things where we haven't figured out what's going on, and we're kind of exposing our unformed thoughts. So I appreciate your forbearance, and it's great to get comments and questions as we go along. We are going to be talking today where this is run 3 at trying to figure out what angular momentum is in the context of our models, and particularly quantum angular momentum, heading for how we understand spins of particles like electrons and photons and things. And for bonus points, I'm predicting that we may have some relations between what we figure out there and the question of where things like electric charge come from. So just to recap, we were looking at the way in which we interpret momentum as a linear momentum as a flux of causal edges through time-like hypersurfaces. And so we're thinking that there's a generalization of that will cover things like angular momentum. We also, last time, were talking about the no-hair theorem for black holes, which says that in sort of a stationary black hole in continuum of general relativity, there is only the mass, the angular momentum, and other global quantum numbers like baryon number are the only things that are sort of noticeable in a black hole. And so that leads us to wonder whether there are analogies between that type of result and the sort of the identicalness of electrons and things. And anyway, so there are some questions coming up there. But I think what we have, first of all, Jonathan has been making progress, I gather, on some thinking about the correspondence, how angular momentum can be derived in our models, and particularly the relationship of angular momentum to various pieces and derivatives of the energy momentum tensor. We talked before a little bit about the sort of the tensor structure of angular momentum. We're sort of used to angular momentum in 3 dimensions, where angular momentum is a vector, but in general numbers of dimensions, it's a rank 2 tensor. There are sort of questions about how everything generalizes in our kind of models, particularly when there isn't necessarily an integer number of dimensions. All right, let's launch here. Jonathan, am I sharing my screen, or do you have something exciting to show on your screen?
Unfortunately, yeah, I don't really have anything exciting to show because what I think I figured out isn't a fundamentally new idea. It's just I think I've cleaned up my earlier thoughts about how about this whole total minus net flux idea and exactly how that works kind of geometrically and algebraically.
Okay, all right. Let me.
And actually, I think your vector plot from last time might be a useful aid.
Okay, let's start off with that. So last time we had, let me just pull it up here. Okay, we were discussing angular momentum, and we had a little very simplistic vector plot here. So should we bring that vector plot up again? I mean, should we recompute that in our new, just to keep track of what we're doing here? So this is just showing something with a curl, so to speak.
Right.
And we can think of that. Well, go ahead. You were discussing. So this is a picture, in effect, looking down a time-like vector, and so this is the time-like hypersurfaces are what is drawn across the page here. This is kind of looking down a time-like vector where the plane of the page is a space-like hypersurface. Is that right?
Yep. Yeah, I think so.
Okay. So explain away.
Sure. Okay. So obviously, our notion of linear momentum is that it's something to do with fluxes through time-like hypersurfaces. So in this particular case, right, we draw a straight line, say, through the middle of this thing, and right, we'd say, what's the flux through that? But and the point I've been making is that somehow that's that's not quite enough, because what we actually care about is the net flux, because if there's stuff going around in a circle like this, there isn't actually any linear momentum. Of course, there's the subtlety that if you look on a sufficiently small scale, angular momentum of this kind will look like linear momentum. But if you take the whole hypersurface, you'll see that it's not. It's actually angular, right? So the point is that in defining that time-like hypersurface, right, the normal to that time-like hypersurface gives us the space-like vector in which we're projecting the relativistic form momentum, right?
So wait a minute, you're saying you have a time-like hypersurface here.
Yeah.
And the normal to the time-like hypersurface is a space-like vector, which is the defining, which defines the time-like hypersurface, but because the time-like hypersurface is specifically the set of things that are orthogonal to the space-like vector.
Yes. Right. So that allows us to compute the linear momentum in a particular space-like direction, which is what we want to do, right? So that's kind of what we're doing.
You mean the projection of the linear momentum? So the way you're saying it is, we've got the thing that we're computing is given a space-like vector, let's call it V or something. What you're saying is we're computing, V dot this field basically. We're computing in which gives us the component of the linear momentum in the direction of that space-like vector.
Right.
Yep.
If that makes sense. Okay. So now, what's different about the angular momentum case? Well, this is where the thing Jose has been saying about having to define planes and things. I think I now have a cleaner way of thinking about this. So now what we need to do, if we want to define angular momentum, it's not good enough just to project in one space-like direction. We actually have to project in a whole space-like plane. So you have to have another geodesic to define the direction of the plane in which you're kind of rotating, and then you sum the total minus net fluxes across all of those time-like planes, and that gives you the total angular momentum in that plane.
All right, I like it. That sounds promising. Okay, so let's think about this for a second. So what you're saying is, let's look at the case where we do have a slightly more convincing. We had this three-dimensional vector plot, right? And what you're saying is that we define we need to actually draw the plane here. We define a plane, a plane defined by, well, no, wait a minute. You're saying we have two space-like vectors. Explain again.
Yeah. So we have to define the plane of rotation, we need two space-like vectors, right? Unlike in the linear case, it's not good enough just to have one space-like vector. So the two space-like vectors define this plane of rotation, and then within that plane of rotation, we're setting up time-like hypersurfaces whose normals lie in that plane, and we're sweeping those round, and we're computing the total minus net flux of causal edges.
Okay, we're going to draw these planes. Sorry, Jose, were you going to say something? Jose, did we just cut you off?
No. I'm following what Jonathan says, and sounds reasonable to me.
Yeah, right. And actually, I should say, so the email that Jose sent just after that meeting, which was about the sort of left-hand side of Stokes' theorem and trying to connect what we were doing to the left-hand side of Stokes' theorem. That's, I think, actually the thing that helped me clarify what I was trying to say, because what I realized was the connection with the left-hand side of Stokes' theorem kind of explains why you have to do this total minus net thing, because to define the quantity at the surface.
All right, should we bring up Jose's mail? Yeah,
we can do.
So go ahead, explain.
Right. So what the left-hand side of Stokes' theorem is really talking about is the value of this quantity at at a two-dimensional surface. That's the thing you have to compute on the left-hand side, right? The notion of causal edges makes it kind of hard to figure out what that quantity might correspond to. But what I realized was, if you have causal edges just going out or just going in to that surface, then that's not the quantity defined at the surface. The quantity defined at the surface is where if you imagine the causal edges are kind of zigzagging along the surface, right? That's the analog of a quantity defined at the surface.
Yes.
Right. So that's the case where you have a total minus, where your total minus net flux is zero, and of course, so that's the quantity that we're trying to compute.
Okay, hold on. So, by the way, Pierce on our live stream has sent through a multi-way system. I'm very happy to see a multi-way system here. So let's just compute his multi-way system. I can't tell by eye what it does. So let's just run it and see what it does.
C goes to A or C goes to P first allows for directionality.
Not completely sure what this is.
Is this supposed to be a representation of a plane, maybe? Is that what, maybe that's what they're saying? I don't know. Pierce, if you could clarify what this is meant to be, it would be helpful.
Yeah, right. It looks interesting, but we need to know more.
Right.
Okay, so I want to understand. I want to start drawing some planes in this picture to understand what you're talking about.
Okay?
Sure. I want to get the projection into. So you want to define two planes, as I'm understanding it.
Yes.
Tell me. So in three-dimensional space.
Well, actually, we only want to define. Okay, we want to define one plane, and then we want to sweep out a family of planes normal to that plane.
Just to make sure I understand, the three dimensions here, are they space-like or one is time-like?
One is time-like, I think, in this picture, right?
No, but in your planes, what you're saying is you define a plane. Okay, give me a plane. We'll just have an infinite plane. How do we define? How does our infinite plane primitive define planes? Passing through these points or in the directions v1 and v2, right? So let's say it's passing through the point 0, 0, 0, 0, 0 in the directions, and those hopefully are those the normal vectors that you're talking about, Jonathan?
They are, well, no. First of all, you're defining the plane of rotation, right? So this is just the two vectors that define the plane of rotation.
Yes. Well, so let's remind ourselves rotation,
which will end up being two of the normal vectors in the other plane that we're going to sweep out.
Okay, let's remind ourselves. Rotation is defined by basically two vectors that it says a rotation takes this vector u into the vector v, right? So we can say a typical rotation matrix in 3 dimensions might be take the vector 1, 0, 0 into the vector 0, 1, 0, right? So if I'm not mistaken, that will be a rotation matrix that looks like that, right? That's going to take any vector in the x direction and turn it into the y direction, correct?
Right.
So the z is the identity, and this is the standard xy rotation, 90-degree rotation matrix. Okay, so rotation matrix, a rotation is all about taking one vector to another vector. Okay, now what? So
right. Okay, so we can use those to define a plane.
We can indeed. So these two vectors here, so these are vectors in which are part of a plane. So they are 2 points. How do we do this? How do we do this? How do we do this? So in the infinite plane case, we could define the vector that define a plane that contains those 2 points, those two vectors, and the origin.
Right. Right.
Is that what we want to be doing?
If that's how infinite plane does it, then yes, that's
well, that's a way of doing it. That's defining a plane with 3 points.
Sure.
Okay, so that's defining the plane through the origin that is in the x direction and y direction. So, for example, if we were to do, I'm just sort of keeping it simple here. If we were to add a z component to this, hopefully there we'll have a plane that has a z component, right?
Right.
And those vectors, just to make the picture clearer, those vectors we will be getting, so it will be a line from 0, 0, 0 to 1, 0, 0, and a line from 0, 0, 0 to 0, 1, 2. That will be an alternative way of defining this plane as a thing that's sweeping out. Yeah, right. Those are those lines. They're a bit. Let me just put something in here that makes them thick and red. Oh, we don't want to do that.
You could use arrow instead of a line. Probably will be clear.
Okay. Okay, great. So those are the two vectors that, starting at the origin, define that plane.
Right,
Okay.
right. Which is kind of which gives at least a tentative answer to your question of like, what is a p-form in our models, right? It's just,
You're saying a p-form is 2GD6 is defined, a 2-form is defined by GD6 from a single point.
Yes.
That go to 2 other points.
I think so.
Okay, so let's actually see one of those just for fun. Let's see what.
Well, I wonder if that's what Pierce was trying to give us.
A 2-form.
I possibly
could be.
Yeah.
Okay, a 2-form. So I mean, we can see a 2-form in a. I mean, this is going to operate at the level of the hypergraph, but you're saying operate it at the level of. I mean, ultimately, there's going to be in a causal graph, but should we look at this? Should we look at this in a? Let's just look at this for fun, just to understand what's going on. Let's look at this in the context of a hypergraph. Okay, so let's pick up our favorite hypergraph here. Let's see if I can get one. Okay, let's try this guy. Okay, so let's just do, let's just do 9 steps or something in this. And okay, so there's our graph. Actually, let me go ahead and get the final state here. And then I'm going to actually draw the, okay, there's the final state, but let's turn it into a graph. Okay, there's a graph. So now we want to start from a single point here, and we're going to pick JD6 to 2 other. I just want to be explicit about what we're doing here. So we're going to pick points. So let's say vertex list of this. Okay, great. Let's sort it just to understand what that's like. Okay, so we've got points from 1 to 320. Okay, so let's pick. So a geodesic would be a shortest path. So let's call it GGG, is that graph. Okay, so now the geodesic would be, let's say, from point 50 or something. We'll say find shortest path in GGG from the point 50 to another point 200. Okay. Aha, okay, right. So I see, because this graph is a directed graph, as our causal graph will be, by the way. Something we should not forget when we're trying to make these things up, right?
Right.
But for right now, let's make this an undirected graph just so we can see how this 2-form thing works. Okay, so now we got that. Okay, so that's the shortest path in the graph from 50 to 200. Let's get the shortest path from 50 to 300, let's say. Okay, now let's draw, let's say, highlight graph.
The first part of those paths are the same.
What's that?
The first 4 elements of those paths are the same. So
well, isn't that an interesting problem?
Yes, right. So we have some degeneracy.
Because that's what we get for trying to do an explicit example.
Right.
So we want the path graphs of these things, okay? And we'll say that. I mean, yeah, that is the life of explicit examples, is that we may not see what we expect to see. Okay, so there we've got, let's make this, how do I do this? Make this thick, do you know? Let's say edge style. All right, well, let me make this a graph 3D as well. All right, so there is our rather unconvincing 2-form. Because what's happened, as you say, is this shares the first part of the GD6.
Right.
Right. Okay. So, but in general, starting from a given point, we will be defining essentially these pair of GD6 will define a plane here.
Right.
And in principle, we can fill in that plane by looking at along the GD6. Is it the case that will make something like one of those, string figure type things by joining every point in one JD6 to every point in the other JD6? Is that true?
Right, I think so. Because you're basically one way you can define a plane, obviously you'd never do this in the conventional geometrical case, but one way you could define a plane is just take the two vectors, and then, as you say, for every pair of points, solve the extremization problem of minimize the distance between those two points.
All right, so this is a more convincing case. So what we've got here is that's the starting point, and this is the analog in this space of what we define here in ordinary three-dimensional space with two vectors defining a plane. And just for the hell of it, what's that?
Right, no, I agree.
Okay, just for the hell of it, I want to fill in the string figure here, just so we see what that looks like. And then we're going to fill that in for the other case. Okay, so the string figure, I reckon, is a table of essentially lines that go, who can help me here? I'm trying to go along those vectors a certain distance. Don't we have some nice functions that let you go, you know what I'm trying to do here? I want to go from somewhere along this line. So what I'm thinking is, what is that function called that goes, oh my gosh, what is it called? Where you go a certain fraction of the way along a line. Jose, you were involved in designing this thing, I think.
I don't remember. Are you thinking of
rescale? I'm thinking of rescale. Go ahead. I'm just trying to get a certain fraction of the way along that line. See what I'm saying? I'm trying to get from 0, 0, 0 to 1, 1, 1. Am I being silly here? I think.
No. I was thinking of angle vector or
Why? Well, look, I'm just trying to draw. You get what I'm trying to do? I'm trying to draw the thing which we would get by saying table. We can do it like this: ij, just line, I0, j, 0j, I goes up to 10, j goes up to 10. Sorry, like that. And then I want to say graphics of that. This, right? That's the thing I'm imagining we're going to do along the geodesic. At every point along the geodesic, we're joining it to every other, we're joining it by a geodesic to every point on the other geodesic. Do you agree?
Right. So you need to get the coordinates of.
Yeah, right. So I mean, in this particular case, let's do it in three-dimensional space. We'd have something like this, and then we'd be saying graphics 3D of that, and that would give us a, that is a plane, right? That is the filled-in plane, so to speak. And I'm just saying we could do that with okay, all right, but anyway, we can. I think it will work. I'm just trying to make sure we have a correct understanding of what a plane is. Okay, and I think
I think this is good. Yeah, I think this is a good idea.
Right. So I mean, we should be able to. Let's just try and draw a plane in our weird, multidimensional space, so to speak. Okay. So what it will be is from every point on what we're going to do is we're going to find the shortest path. So from every point here to every point here, what we're going to do is we're going to find the it will be some outer product. Okay, so we've got those points there, and what we'll want is the outer. Am I right? We want the outer find shortest path of GGG, comma #1, #2.
That won't be a problem if the shortest paths are the same, not the same length, will it?
No, it's an outer product, so it will do the right. I think it will do the right thing.
Okay.
Except that I got something wrong here. Let's see. What did I get wrong?
Why do you have a list around the find shortest paths?
It's wrong. That's what I got wrong. Thank you. Okay, So those are the GD6. Those are all the GD6. So what we're going to do then is for each of those, we will say path graph of those. And I think we want to do a catenate around this to bring it down to the right level. Is that right? Okay, so now what we want to do is we want to say for this thing here, anybody know how to do in a highlight graph? Does anybody know how to highlight the just that path graph there and not another, how to make it thick, just that path graph thick? Oh, well, okay, all right. Well, let's fill the whole thing in here then. Okay, so what we want to do is the join of this to.
You can wrap the thing in a style.
I can wrap that shortest path in a style.
Yes, apparently.
Do I have to wrap the path graph in a style? I think I'm going to have to wrap the path graph in a
I think you do. Yes, yes.
Let's first of all see if this works. Okay, that worked. Brilliant. Okay. So now we have to add the catenation thing to that. So then we will take this and we will say join that to the thing with the giant catenate here. Okay, what just happened here? Oh, we forgot the path graphs here.
Right. But that's all the points in the plane, and that doesn't look too bad. Or in the plane segment.
Okay, so now what you claim, so what we've got, I don't know why these things look, that's pretty funky looking. Explain. Okay, so where was the original point? The original point is the intersection of the reds and yellows, isn't it? Yeah, I'm a little confused by what happened here. Because what I would expect is that there's a large number of, I mean, there seem to be a lot of shared GD6 here.
Yeah. Well, this might be a particularly pathological hypergraph. I can't really tell what's going on.
Should we try for a simpler hypergraph? Should we try for some kind of grid graph? That may also be, let's try for a 3D grid graph, okay?
Yeah.
So,
although it's not, I mean, it's just going to look the same as the Cartesian case, as you know.
I agree, but I still want to see it actually work.
Yeah.
Because sure. I'm always suspicious of these things. Okay, so let's say, let's call this make plane. And we're going to have a graph GGG, and we're going to have an initial point I0, and then we're going to have, we need to have two other points, right? I0, I1, I2, otherwise known as a plane is defined by 3 points. This is just a generalization of that idea. And now we want to say that is I0 is there. That is I1, I2, I0, I1, I0, I2. And it'd be really nice if we could figure out how to get this thickening to not affect the second. Well, okay, let's worry about that in a minute. Okay, let's just check that this will. Okay, so let's try saying make plane of grid graph. Actually, we still want to say index graph of grid graph, let's say 10, 10, 10. Because that's going to be a 3D grid. The index graph of that, and let's start with the points, I don't know, 10 cubed is 1,000, so let's start with like 500. Let's go to 700 and 300. Ugh. Oh, we have something, but it was very pathological. Okay, so we really want to have, what is the center? How do we find the center of this graph? Let's try 100 to 200 and 300. What is going on? Why are they sitting down at the bottom there? Oh, maybe the hundreds hurt it, because maybe it's in multiples of 100.
Yeah, it's a divisibility issue.
Right, so let's try 297, or no, 285, 625.
This is how you know it's real science.
What?
We're just
just making up these numbers. Okay, so hold on. The one issue here is that I'm not happy with the fact that we don't have thickening. Right, so this is not very convincing. I don't see a good. I see the two lines there, but I don't see a convincing sort of cat's. Oh, I see. It's because it's Manhattan distance. That's the problem.
Oh, it's just following the same lines. Yeah.
Right. So we have to take a Voronoi. We have to take some kind of Voronoi decomposition of space where we have some randomness to it.
Or can we not just request more shortest paths?
Maybe.
There is an option to do that.
Yeah, Seth is suggesting changing the opacity, which is a good idea. And let's see how we would do that.
Yeah, good idea.
So how do we do that? We'd have the edge style. Oh, I see. What we want to do here is we want to make the GGG not its original GGG, but we want to say with, let's call this hackery. I'm sorry, this is too bad. Make plane there with GGGG. With GGG equals, and then we want to say graph GGGG edge style goes to opacity 0.5. That's that graph.
Another possibility, although it's kind of a hack, well, sorry, not kind of a hack, it is a hack, is that we when we do the second find shortest paths for the outer product, we could convert the thing to a directed graph so that we can only get, so that, in effect, we outlaw going back along the two.
Yeah, I understand. Why did this not change the opacity? I don't understand that. Are we going to need to get, Seth is suggesting graph center is also suggesting directive. Do we need this as a directive? Shouldn't. Humphrey Humph. Well, okay. Let's try, forget this particular graph. Let's try this graph. Let's try a higher iteration of this thing here. So let's try here, that was 9 steps. Let's go ahead and try, I don't know, let's go to 11 steps. No, let's go a little bit further. Let's go to 12 steps. Okay, now we want to do this thing here, make plane. Actually, I want to do vertex count of %47 to just know how big this is. Okay. Interesting year. Okay, so now make plane %47. Let's start with node 1000. Let's go to node, let's say 500, and to node 1500. All right, let's see what's going to happen here. Okay. All right, so there is our faux plane.
That's actually quite nice.
It is quite nice, yes. All right, so this is what a plane looks like. This is the generalization of a plane, basically. So welcome to a 2-form. I mean, so this is a 2-form. And what we're going to be asking is various features of, the real case is this in a causal graph, right? Rather than this in a spatial hypergraph.
Right. Although, I mean, the actual plane of rotation is defined in the spatial graph.
okay, so how do we go from that to okay, so this is the plane in space-time, in the spatial graph, right? Well, this is actually in space.
Yes.
This is the plane in space. For ordinary angular momentum, we want a plane in space, don't we? We don't want a plane in space-time.
Yeah, exactly. That's what I'm saying. So this is the plane of rotation. It's just that now, in order to actually compute the angular momentum, you then have to sweep out a time-like plane.
All right, so what you're saying is, in order to compute, so if we were computing linear momentum, we would define a vector direction here, and then we would sweep that vector direction sort of downwards in the time-like direction. That would define a space-time plane, and then we look at the poking through of that space-time plane of causal edges.
Exactly. We pick a geodesic in the spatial hypergraph, and that's the normal of the time-like plane through which we compute the linear linear momentum, the flux.
Is it the normal, or is it just? Is it like a curtain rod type thing where the plane kind of hangs down from that geodesic?
Well,
I think we could define it that way.
That would give you linear momentum along that vector.
Yeah, exactly.
At every point along the vector. But actually, what I'm trying to describe is computing linear momentum at a point. Right? Suppose you have a point in space.
Fair enough.
Okay. Linear momentum.
Right. So the limit for what you're saying, the limit is okay, but I'm still a little bit confused about what's orthogonal to what. So this plane, drawn in arbitrary dimensional space, so to speak, is now what do you want to do with this plane to find the angular momentum?
Right. So you can imagine the case where, okay, so going back to to the linear momentum case that you just described, right? So we could define a time-like plane whose normal is one of these vectors or the other vector, right? But we could also define.
Okay, hold on. The time-like plane. Let's be explicit in this picture. Okay, we've got a vector in the hypergraph. Okay, vector, aka a geodesic in the hypergraph, right? And now what we want to do is we want to define the family of orthogonal geodesics to that geodesic.
But not in this graph. It's a family of orthogonal geodesics in hypergraphs, adjacent to it in time, not in space.
Let me see if I really understand that. So to define that collection, let's see. So the causal graph knits together the spatial hypergraphs over time.
Right.
We've never had, it remains one of the things we need to do is to figure out how to visualize a series of spatial hypergraphs stacked up in time. We don't know how to do that right now.
Right, but the causal graph gives you a way of computing it, as you know.
Right, absolutely. But we have a way. Actually, that raises the question: why isn't there a way of doing visualization, which is essentially just you compute the causal graph first, and then you kind of hang spatial hypergraphs on different layers in the causal graph? Why won't that work?
I think that's a reasonable approach, and for doing maximally stable graph visualization, what you're really asking for is the flattest foliation of the causal graph that you can construct.
Yeah, why didn't we do this? This is obvious. This is what we should do.
Well, yeah, there was a summer school project on stable graph visualization either last year or the year before. I can't remember.
We didn't know about causal graphs then.
Well, we did, but we hadn't made that connection. But we should do that this year.
No. But we should do that before then, because that's the obvious thing to do, to be able to get a stable visualization of these graphs changing with time. And I really want to see that in VR in particular, being able to sort of be inside one of these things where you can see in 3 dimensions, right? So because that causal graph, really what we want to do is we want to see the spatial hypergraph changing with time in 3 dimensions.
By the way, this would be officially the weirdest interpretation of the cosmic microwave background that I've yet encountered.
What?
That the CMB defines the rest frame in which hypergraph visualization is maximally stable.
Yes. But so your point is that one wants the most flatly foliated causal graph to give one the thing which most convincingly just represents essentially time steps in the evolution of the spatial hypergraph.
I think so.
Right.
That's my intuition, at least. I don't know.
Yeah, no, I think that's right. I think that's right. So use the, so this is a time visualization of the spatial hypergraph. Somebody should do that out there. We don't need to do this. It's somebody. Okay, so start from the causal graph. Start from a well-foliated causal graph. Somewhere we're going to have, by the time we have well-foliated, we're going to be talking about exfoliation and all kinds of puns that just go crazy. But anyway, never mind. Start from a well-foliated causal graph.
When you reconstruct hypergraphs from causal graph foliations, we should totally call that exfoliation.
Yes, right. So okay, start from a well-foliated and hang the spatial graphs off that. All right, but what we're talking about right now is a series of spatial graphs where we are connecting those spatial graphs through the causal graph, and this geodesic will become some other geodesic and some other spatial graph where the points in this geodesic, in this foliation of space-time, will connect to points in another geodesic in sort of its successor in space-time, in time rather. Right.
I mean, yeah. The way I would think about it is, or the way I personally think about it is that you define your time-like hypersurface, and basically every normal vector to that time-like hypersurface is a version of that geodesic, just just sort of spread out in time.
Every normal vector. So hold on. I'm still trying to get the picture here of what's going on, because I'm still, then we're going to generalize this to thinking about this plane. You're saying, no, say that again. I mean, you're saying, given this is a space-like geodesic here.
Yes, right. And the point is every space-like vector is orthogonal to a time-like vector.
Indeed.
Right. So we can think of this time-like hypersurface in the causal graph as being a surface with the property that this geodesic is normal to it.
I know, but
extended in time is normal to it.
Right, but then we've got two kinds of normality, right? We've got this space-like vector is defining a direction. Mm-hmm. We've then got a time-like vector orthogonal to this space-like vector.
Yep.
And then we've got the flux through the surface defined by the time-like vector.
Yes,
which will be going to reconstruct again a space-like direction. So in the end, the net of the whole thing is that roughly what we're talking about is momentum flow along this geodesic.
Pretty much, yeah. Well, I mean, but actually, it's not just along that geodesic. Well, it is for the linear momentum case, but momentum flow actually along all geodesics in that plane.
Exactly, right. And that gives us, but roughly, this geodesic defines a direction. Your procedure, this procedure of orthogonalization and double orthogonalization, so to speak, mm-hmm. puffs this out from being a single vector in that direction to being a whole plane of vectors all lined up.
Right.
And then what we're saying is, what we're looking at is the dimension going through, we're looking at, okay, so I'm just trying to understand. So then in the end, it's the linear momentum projected along the parallel directions defined by this vector and its parallels.
Right.
I mean, what you've given is a procedure for essentially doing some kind of parallel replication of that vector.
Right.
Which, by the way, we should try and explicitly do. So, I mean, basically, we're doing sort of double orthogonalization. So we say we start. We don't have orthogonalization as a noun. That should be a spelling word. Let's send it in. Okay. Okay. So we start with, e.g., for linear momentum. start with a space-like vector. Space-like vector defined by GD-SIC in the causal graph. In the spatial graph. Okay. Then find the time-like vector. Find the time-like vectors that are orthogonal to that space-like vector. Then find the flux through the surface defined by that family of time-like vectors. Yes?
Right.
Okay, I think I understand finally. All right, now let's do the corresponding case here. And we've had more suggestions about this from Pierce here about this this multi-way system, and I really want to look at this.
Right. I think he's constructing. I think what he's doing is constructing a way of visualizing these planes.
That sounds interesting. That sounds highly interesting. Okay.
C is a plane of time. A is its own plane. P is a plane. The cross product of C and either A or P should produce the third plane.
Okay. Well, let's run it. Oops. Okay. Now explain this to me. Okay, C is a plane of time. Oh, so this is a multi-way graph that explains the possible rotations from one plane to another.
Right. I think so.
Right. So this is effectively a multi-way graph analog of. It's like if you had got the actual planes, you could apply a rotation matrix. This is okay. Claim.
This multi-way like, SO3.
What's that?
Multi-way SO3.
This is multi-way SO3. As otherwise, which is very interesting, actually. So the matrices, the rotation matrices, will be a matrix representation of SO3, but this is a representation of SO3 in terms of words, I think.
Right, right. Yeah, that's a cool idea.
Comments on that? What is the representation of SO3 in terms of words? Did we lose Jose?
No, here the standard representation of SO3 in terms of?
In terms of words, as opposed to the matrix representation.
In terms of words.
I mean, like for example, I mean, if we have the icosahedral group, how do we get the icosahedral group? If we say finite group data.
Yes, but SO3 is not finite.
I know it's not finite. I know it's not finite. So this is the beginning. Maybe this is part of the Lie algebra of SO3. What do the words? I mean, usually you don't talk about words in the Lie algebra because the Lie algebra is infinitesimal. But you could think about the infinitesimal rotations and the relationship between infinitesimal rotations represented as, you know.
Are you basically asking for a verbal description of the like orthonormal basis of little SO3?
Yes, but not verbal. As in what I'm asking for is a calculus of the infinitesimals that represent the infinitesimal rotations in the Lie algebra of SO3.
Well, the little SO3 Lie algebra, I mean, it has a standard orthonormal basis. The omega 1, omega 2, omega 3 matrices.
No, that's true. Right. So then this would be potentially, then you could set up the word problem in terms of omega 1, 2, and 3.
Yes.
And then this is potentially a representation of that, which is quite interesting.
Yeah, I agree. I think we should do more of this.
Yes. I mean, this is good. This is very interesting. Okay, but let's return for a minute before we get. This is the sort of group theory question mark version of this.
But by the way, if we do manage to get basically a multi-way analog of the orthonormal basis of little SO3, this may answer your question about the connection to moment maps.
Okay, so you're claiming that the speculation is that this is a representation. Is it the Cayley graph of little SO3, or is it something different? I think it's the Cayley graph.
It's certainly related to the Cayley graph. I'm not sure if it is. Well, sorry, the causal graph wouldn't be, but the states graph would be related to it.
Let's look at the states graph of this thing. What is the causal graph related to?
I don't know.
Okay. Do we know the algebra do we know the commutation relations of the algebra of SO3? We should know them. In fact, I think I even know them. I mean,
This should be cyclic.
Yeah, this doesn't look crazy.
Interesting, very interesting. Okay. By the way, if you have a states graph that is, let's just ask that question. If you have a states graph that is a Cayley graph of a group, what is the causal graph?
Yeah, I think we tried to answer this question a while ago, and I didn't have a good answer, and I still don't.
Right. I mean, okay. Let's go back. Let's go back to what we were doing before, though. Okay, so because we're really getting somewhere here. This is exciting as far as I'm concerned, at least. Okay, so linear momentum. Again, we start with a space-like vector. Otherwise known as a geodesic in the spatial graph. We find its time-like. We sort of create, to find its time-like extensions, what we're doing is evolving the spatial graph and asking for things which are the evolution of that geodesic in time, so to speak.
Right.
And then we're asking, given that structure, we're asking for the causal graph created from those points in the evolving spatial graph, what the edges of the causal graph, which effectively are saying what transfer of information is there from essentially one side of this. Yeah, what we're asking for is the transfer of information parallel to this geodesic. That's the ultimate question, right?
Right.
The flux of causal edges along the direction of the geodesic of the quote space-like geodesic is the rate of information transmission, effectively, is the rate of activity transmission, so to speak, along that direction.
Right. Although I mean, I think it is useful to clarify whether we're talking about total or net. I think that is important for clarifying.
Oh yeah, it's very important. Right. But so what we're talking about here is the net flux. That's what's
right.
giving us the rate of information of activity transmission along that direction. It's the rate of moving activity information along the direction of the space-like geodesic.
Exactly.
Okay. Now we understand linear momentum. Okay, let's keep going. Now we're talking about this thing defined by two geodesics, which is going to define. Okay, so let's walk through that one. So, what is the analog of this statement? That a flux of causal edges along the direction of the space-like geodesic. What's the analog of that for this plane defined by two geodesics? What's going to be the sort of the net thing that we think angular momentum is associated with? Is it activity that exists in that plane somehow?
Well, it's activity that's going along the plane, but it's a subtle kind of activity that makes it distinct from the linear momentum activity, right? It's the activity that happens without achieving anything, so to speak, because there's no net movement.
I understand. So it's activity that I think it's activity that somehow remains in that plane and sort of circulates around in that plane.
But you can have linear momentum that remains in the plane too, right? Because it can just keep moving along the geodesic.
No, I understand that.
So it's somehow futile activity confined to the plane.
Yeah, well, it's a circulatory activity, much in the way that we had this up here. This is activity that has no net, it has no net transfer of vector, whatever we define, momentum, whatever that we define here, there's no net transfer. So what we want is something where we're defining the activity that exists in that plane, but never manifests itself as net activity. That's
exactly. It's futile activity. What I've been trying to do this time is kind of, because I agree that your picture about it, it's just circulation of causal edges is right. But what I've been trying to do is come up with a purely graph theoretic way of defining what we mean by circulation.
Yeah, well, I think that's what we want to do, right? That's the goal here. So what you're saying is, it is essentially activity in that plane that does not lead to a net flux.
Yes.
Okay. And it leads to a net flux in no direction, basically. In other words, there is no linear momentum associated with it.
Right.
So what you have to say, okay, so let's write down what the claim is here. Okay, so we're saying this angular momentum is within the plane defined by 2GD6. It's within the plane activity, within the plane activity transmission that has no net, that leads to no net transmission in any direction. In any direction in the plane. It could lead to net transmission in some other direction that has nothing to do with the plane. So that leads us to the question of the relativistic transmission. Okay, so I'm buying this. This is I'm sure this is right.
Yeah, so it can lead to transmission in time, but not in space.
Exactly, but now the killer here is what is the how does the angular momentum transform under Lorentz transformations? Let's not get to that yet. Let's define it very precisely, and then we're going to see what it implies for Lorentz transformations, because that's kind of a check on whether we've got the right answer here, right? Because this is now, so what you're now claiming is that it is total causal edges within this plane, but it's total causal edges minus all net flux. How do we define all net flux? Is all net flux related to divergence or what? What's the analog in vector analysis of what we're trying to do here? So in other words, we've got this function, we got this vector function here, and that vector function is
well, the analog is net flux in vector analysis. It's the thing you compute by taking the integral and then subtracting off the integral of the absolute value. Oh no, sorry, the other way around.
What do you mean net flux? I mean, flux normally. So normally in vector analysis, in three-dimensional vector analysis, you've got. I mean, the thing that will be relevant here is the curl, and what we're saying is what is the relationship? So this vector function has a curl, obviously,
right?
And rarely use vector analysis in our fine system, but
the point.
Yeah.
Sorry, the point I was trying to make was that when you compute a flux integral in vector analysis, you're generally computing a net flux. You can compute a total flux by integrating the absolute value of the vector field.
I have used the curl function in our system so unbelievably rarely. Do we have a generalization of the curl function to arbitrary dimensions? That will be a Jose question.
Yes.
We have the Hodge dual.
Exactly, at least through Hodge dual. But perhaps curl itself already does it.
Oh, okay. Oh, we have tensor wedge products as well.
Right. So curl is constructed on top of this structure of antisymmetric tensors. So yeah.
Right. Okay. But so let's go back again to the thing I didn't understand.
Right.
Okay. So Jonathan is trying to define what angular momentum, and by the way, whatever definition you give, I'm going to apply it to fluids. And I'm going to see if it gives the right answer.
Right. Well, But by the way, I mean, sorry, just on the, you see my point about vector analysis, right? That when you compute a flux integral, right, it's a surface integral over the vector field dotted with the normal vector with respect to the surface.
Yep.
Right. That gives you a net flux naturally. That's what most people mean when they talk about flux. But you can also compute the absolute value of that dot product, and that gives you a total flux. And so what we're talking about here is the absolute value integral minus the net integral.
I know, but this absolute value thing, I'm just not very familiar with. I mean, that's not what one usually does. If one's looking at the electric field or something, so you're talking about looking at essentially the intensity of the electric field, which I'm just not very familiar with. I mean, in standard electromagnetism vector analysis, you're not typically doing that. I mean, it's like quantum mechanics. You take the intensity at the end after you've computed your diffraction pattern or whatever.
Mm-hmm.
But so that's what I'm a little bit confused by. You're saying that we could take the integral of the absolute value, basically, of, is it the absolute value or is it the absolute value squared and so on?
For a flux integral, I think it's just the absolute value.
Yeah, it is. I mean, but this idea of total flux is very confusing to me, because normally flux is a vector quantity. Am I being confused, Jose? Do you? This is an electromagnetism question. We've got the wrong, the wrong set of people here.
Well, you talk about, okay, my understanding of electromagnetism is you talk about both net and total flux, right? You talk, if you're talking about a surface around a charge, if you have a charge Q, right, yeah, you talk about the total flux being Q over epsilon naught.
Sure, and then Gauss's law tells you what the flux. I mean, it's a,
yeah, right. So I think that's a trivial case in which you get the concept of a total flux in electromagnetism.
All right, but in that case, it's a divergence.
Yes.
The total flux is the integral of the flux per unit area over 4 pi and over the two-dimensional surface there. All right, yes. Okay, let's go back again. So I want to know for this, I mean, given some function here, x, y, x minus y, y minus x0, for example, what is the actual computation that you want to do to compute what you think is the angular momentum?
Okay, so what we want to do is we define a surface, which in this case is just a line, right?
Okay.
And then we want to integrate this vector field along that surface. So in that case,
so what you're going to do is dot it along. You would define a line.
Yeah.
A line is defined by some ax plus b type thing in this particular case. Then you're going to dot this function with the projected along that line.
Well, we're going to dot it into the normal, right? We're going to dot it into the line that's orthogonal to that.
Fine. Yep.
But actually, in the end, it's not going to matter, because then what we're going to do is we're just going to sweep that line through 360 degrees, sum over all of these things, and that will give us our quantity. Okay,
we did something like that last time, and
yes.
Let's look at that. And I really want to see the analogy with fluid mechanics.
And we got an answer of 54, if I remember correctly.
Yes, I remember that. Yeah. Okay, but let's look at this in. Okay, let's remember what we did last time. How was it? So this was this function dotted with the unit vector. Actually, that's not the unit vector. That's within a disk. That's not a unit vector. That's a vector that lies within that disk. What do we actually want to do? Do we want to do it on a unit vector?
I think so, yeah. We want a unit normal.
Okay, so if that's the case, then what we actually want there is, cosine theta, sine theta, I think.
Right.
So then we want to integrate that over. So we're integrating over x and y, and then we want to plot that as a function of theta, if I'm not mistaken.
Yes, and actually we only need to rotate. We only need to go from theta to 0 to pi. because the line is extended, so to speak.
Yes, it's an infinite. It's an infinite line. Okay. Drum roll. Why is this so slow? What is it computing here? Is this trying to compute some crazy analytical thing? No. Okay.
54.
Well, that's our 54 again. But this is, so probably rather trivially, this is, let's just see. Isn't this an analytically doable integral? Isn't this a straightforward integral? Why it's taking it so long.
I'm always suspicious of absolute values in integrals.
Yeah. Absolute value is a horrifying bear. Yeah. Okay. Right. Yeah. Planumbra on live stream is saying, once the model is properly refined, it should be possible to create a 3D animation to illustrate the ideas like the phenomenon of general relativity and quantum mechanics. I agree. I mean, that's what we really need to do. And you know, to get these graph evolution things, then get them in VR and so on. I mean, there's a great movie to be made of of showing how one is, you know, how all the branches of quantum mechanics work, following one branch, following how that evolves in space-time. And this is unbelievably slow, and I'm going to kill it. Okay, so let's try to understand what we saw here. Okay, so what is this? This is you're saying this is the total flux through a line at a particular angle.
Right.
Okay.
But what we actually want to do is sum over this. So actually, you know, we want to integrate this quantity again.
So we want to integrate over theta.
Yes.
Okay, so we want to do another integral here. So we want to say n integrate there over theta to 0 to 2 pi, like that.
Right.
Wow, funky. Okay.
Right. So, but that's only giving us the total flux, right? But we also, in principle, we should subtract off the net flux. Now, in this particular case, we happen to know that the net flux is 0, but obviously we don't know that in general.
Right. Okay, but the more general case. Okay, so I'm still trying to get. Okay, let's talk about the analogy with fluid mechanics here, because
sure,
it should be the case that the angular momentum is related to vorticity, right?
That sounds right. Yeah.
And let's see. I'm going to look up.
Vorticity is 1/2 the angular momentum of the fluid about each fluid's lump, around the lump of its own center of gravity.
Okay, but the definition of vorticity is it's the curl of the fluid field, isn't it?
Right. Yeah, of the flow field.
Right. So vorticity equals del cross. I don't even know how to do a cross here. Del cross v, where v is the velocity field. And the angular momentum, if I remember correctly, you can get by integrating the vorticity. Because that's the analog of what we're talking about here. Now, I mean, the thing that I'm about to spring on us is quantized, the quantization of vorticity in superfluid helium, which might have some, what's that?
Fair enough. You're big on this superfluid helium stuff.
Well, I am, because I think that may be an analogy to what's happening in the case of spin.
Can I offer an alternative suggestion about how spin works?
Yeah, but let's just home in on. Okay, we're sort of there in terms of understanding. I mean, the intuition is the vorticity, which in the case of a fluid is a curl, and the curl is with respect to a particular axis in 3 dimensions. The curl will give us a 3-dimensional vector field here, right?
Mm-hmm.
And then the angular momentum how does this work exactly? This curl is a vector, right? The angular momentum at any point in the fluid, we're integrating over some small lump of fluid, and we're integrating this vector, and we're then going to get this vector angular momentum at some point in the fluid, right?
Right, right. I'm seeing a bunch of people here saying that vorticity is twice the rotation vector, but I don't know how general that is.
Well, it's probably in 3 dimensions.
That's true.
Right. So the next question is in relativistic fluid mechanics, what's the generalization here? What's the generalization of vorticity in relativistic fluid mechanics? Because it isn't a curl anymore, presumably. There's presumably a Lorentz invariant analog of vorticity.
Mm-hmm.
What is
it's still probably an antisymmetric tensor. It's probably, if you have a vector fluid V, you take a gradient of that, and then, yeah, it's probably the epsilon contracted with that, which leaves 2 other vectors, indices.
I'm just looking at some.
Okay, I've got the equation.
There's some random paper I just found here about relativistic fluid mechanics. So
it's 1/2 covariant mu nu minus covariant nu mu mu, where mu is the momentum.
So you're saying the relativistic analog is,
so if mu is your momentum vector, then the vorticity is
mu. Let's not have mu be a momentum vector. That's going to be ultra confusing.
Okay, that's
the momentum vector.
Fine. That's their choice of terminology.
Okay, so wait a minute.
Yeah, go on.
No, so what's the formula then?
So the vorticity is as Jose said, it's an antisymmetric tensor omega mu nu of the form. Oh, okay, wait.
Okay, so we're talking the vorticity is some kind of omega mu nu, yes.
Yeah, which has the form 1/2 covariant mu.
What do you mean by covariant mu?
As in covariant derivative, covariant derivative operator with lower index mu.
Oops. Yeah.
T nu.
T as in the energy momentum tensor.
Wait, what are we calling our momentum vector?
P.
Oh, P. Okay, fine. P nu. That's okay. That's better. That's better terminology. Minus covariant nu P mu.
Covariant nu or mu?
Nu. P,
okay.
P mu.
And the first P is also nu.
Oh, yeah.
What are you saying? P what?
It should be P nu.
Oh, yeah, in the first one, right, to be symmetrical. And I'm sure that 1/2 goes outside the whole thing. I probably did. Okay, that makes decent sense.
Mm-hmm.
Okay, so the analog of that here, I'm a little confused because the curl, how do I understand?
It's the same thing. So you can write the first formula exactly as the second one with delta I pj, and then you contract with epsilon ijk to give a vector back.
Okay, fine. All right, so these are, okay, so the volume integral of this thing over some region gives the vorticity tensor, rank 2 antisymmetric tensor, which in 3 dimensions corresponds to a vector, and which in our case is, see, I'm trying to understand these derivatives because I think we can probably get to these derivatives pretty directly from looking at the flux. What is the analog of this in terms of, isn't that derivative a flux quantity? Isn't each of those derivatives a flux?
I don't think so.
You can't think of it as a gradient.
I would say this is more like circulation again. So this antisymmetric ordering of indices is going to be giving you local planes of rotation.
Yeah.
These are the two forms we were always discussing.
Okay, fine. All right. So I think I'm sort of convinced what the analog of angular momentum is, which again, let me try and say it again. It's the total activity that is essentially localized to planes defined by pairs of GD6. And its local activity which has any center of mass motion effectively, but its center of mass motion along any direction subtracted from it, right? It's actually just center of mass motion. It's the thing in that plane with the center of mass motion subtracted. Do you agree? Why does it matter? What's the thing in the fully general case without defining a plane? What is that quantity with the center of mass motion subtracted?
It's some kind of directional angular momentum, I would argue.
Okay, so ordinary angular momentum, you say, is defined by a plane, defined by 2GD6. And ordinary angular momentum is associated with rotation within that plane.
Right. But with the linear momentum, just like in the linear momentum case, you could define a quantity that just involved projecting in a space-like direction, and it would give you some directional angular momentum quantity.
Sorry, what are you saying? In the linear momentum case, right? You're saying
I'm saying that you could define a directional angular momentum by analogy with the linear momentum case. It's just that we don't happen to do that, right? We actually want to smooth it out by integrating that quantity over a whole plane. But in our model, there's no reason why you have to do that.
Right. And for particles, when we're looking at helicity, what we're interested in is the angular momentum orthogonal, effectively where the axis of relevance is the direction of motion of the particle.
Right.
So how does that relate to this? So we've got these two directions. We've got these two GD6 defining this plane. And the thought is that then that plane is somehow orthogonal to the direction of motion of the particle. There are many planes orthogonal to the direction of motion of a particle in beyond 3 dimensions.
Right. That's the notion where you have net flux in a particular space-like direction, but orthogonal to that, there is there is no net flux, or there is reduced net flux because you have angular momentum.
Yeah, I understand. So what you're effectively saying is the particle is tooling along with its linear momentum in a certain direction, but in the orthogonal directions, there's also things happening around the particle, and those define its spin.
Right.
So how does it relate to the
helicity.
Pauli-Lubansky vector business for relativistic angular momentum? I bet this direction, because in 3 dimensions, it's going to be somewhat special because you've used up all the directions by having the direction of motion of the particle and 2 orthogonal directions defining this plane. What is the definition again of the Pauli-Lubansky vector? That's a...
Right, so precisely in 4 dimensions, 3 + 1, you have the momentum, the 2 directions of the plane of rotation, and the missing one is the Pauli-Lubansky.
So if you go to higher dimensions, so this is, so we're now looking at relativistic angular momentum. So can I, okay, so you're saying that the degrees of freedom are linear momentum, then angular momentum, and then this Pauli-Lubansky vector, which is, why is that even a vector in 3 dimensions?
Well, I don't agree with this classification. So you have linear momentum.
Yeah.
No, sorry. Yes. So yes, so you have P mu, then J mu nu, and then W mu, and these things
Okay,
are
so
following.
P mu, P mu. Oh.
Well, the way I would think about it is, you have orbital angular momentum, the relativistic thing, and then you have an intrinsic spin, and the Pauli-Lubansky vector is a pseudo vector that incorporates both quantities.
Fine. Okay, so wait a minute. We got P mu. You said you have J mu nu. And the third piece is that W thing, right?
Yes.
Which has how many legs?
1 in 4 dimensions.
Okay, but what happens in any number of dimensions?
It will have more. So this will be n minus 3.
D minus 3, because you've used up, I didn't quite understand. You've used up three indices on P mu and J mu nu. Is that right?
Yes.
So I don't understand why my classification is wrong here. I mean, the P mu is the linear momentum.
Yes, I was confused by the fact that effectively angular momentum and Pauli-Lubansky are representing nearly the same thing, because you can construct one from the other, knowing P.
Well,
Okay.
Also the P is not linear momentum, the P is form momentum.
Yes. So
Okay.
what's the difference between those?
Well, it has another component, but let's talk about, okay, so one of the neat things that we found happened in momentum defined as flux of causal edges through time like hypersurfaces is that we got the relativistic transformation of energy momentum from it. Okay, so a little bit of a drum roll here. Let's figure out what the relativistic transformation of our now supposed meaning of angular momentum is. How does it transform under Lorentz transformations? And first of all, what is its 4 vector? Is it in a 4 vector or something else with other things?
Well, I would say that the way to transform angular momenta in relativity is to apply an independent Lorentz transformation to each of those 2 indices in J mu and nu.
Okay. So that saying that effectively in our plane, you're applying 2 different boosts in that plane?
Not too independent. It's the same boost, but twice. 1 to each direction, if you want. Yeah.
Well, so wait a minute. So if we think about that in terms of reference frames, you're saying that if we have drawn the, you're saying that in our space-time, wherever our space-time is, wherever it is, let's go find our space-time. Okay, here it is. Okay, so this is our plane, rather bizarrely represented here. You're saying, oh gosh, we need the space-time version of this.
Well, all that's happening is that, to boost a plane, you have to boost the individual vectors that define it.
I understand, but you're saying that the foliations of space-time, this plane exists in within a particular time slice. Okay, but I'm trying to understand, as we tip the reference frame, okay, with this definition of angular momentum, what do we mix in as we boost the angular momentum? See what I'm saying? What is the angular momentum in 3+1 dimensional space? The angular momentum is a 3 vector. I mean, is a 3 vector, and in general, in d-dimensional space, the angular momentum is defined by this rank 2 antisymmetric tensor.
Right, but what you're mixing in is the moment of mass polar vector.
What is moment of mass? What do you mean?
So to go from the angular momentum pseudo vector that you get out of classic, non-relativistic mechanics, the x cross p, the additional term you have to add to get the 4 angular momentum in relativity is this moment of mass. What you have to combine that with in order to get the angular momentum antisymmetric tensor is this moment of mass pseudovector, which is the boosted version of the center of mass quantity.
Moment of mass. I've never heard of moment of mass pseudovector.
Sorry, it's not it's a polar vector, not a pseudovector. I'm sorry.
Otherwise known as an axial vector.
Right, or just a vector.
Well, in 3 dimensions, just a vector, right? But it matters whether it's an axial vector or an ordinary vector, doesn't it?
Yes, yeah, in general.
It matters to the parity transformation of it, for example. Okay,
Right,
so what do you mean moment of mass? What is that?
So if you take the center of mass of your system,
Yes.
right, you take that vector and you apply a Lorentz boost, that gives you this moment of mass polar vector.
Okay.
And so the combination of the angular momentum, the non-relativistic angular momentum pseudovector, which is this d-1 quantity you're talking about, and the moment of mass polar vector is what defines the antisymmetric relativistic angular momentum.
So is this moment of mass, this is relative to a rest mass, is that correct?
Yes, I think so.
All right, let's walk through that analysis situation, okay? Because what that's then claiming is that the other component that we are mixing in through boosts is a rest mass. And our definition of rest mass we have in terms of energy momentum, right?
Yes.
So let's see if it's the same.
And it doesn't seem implausible that would happen given the geometry of what's going on. You're basically mixing in space-like projections.
What do you mean? But specifically, what
rest mass is is a space-like projection. It's it's a projection of some quantity through a space-like hypersurface, right?
Yes.
So all you're saying is when you make the Lorentz transformation from a pure time-like plane, you're mixing in certain space-like projections.
I understand, but that's cool if we can show that the angular momentum, that the moment of mass that occurs in the angular momentum angular momentum rank 2 tensor, is the same mass that occurs in the energy momentum formula. That's not obvious. I mean, that in relativity, I don't know why that would necessarily be true. Right? In our model, we don't have any choice. It's going to be connected because we've only got the causal graph, and everything has to come out of that.
Mm-hmm.
Justify why in relativity, why the other element of this rank 2 tensor is mass. Other than that's what you need to get the non-relativistic limit.
I think it's not really mass. It's more like the initial position. So I think we need to write this to understand it. So if we have x mu p nu.
Okay, wait a minute. You're saying x mu
p nu.
Hold on. I am not experienced at typing things, and I don't usually type formulas. Okay, x mu p nu.
Use exact notation, which is xa p minus p, and then it's minus means lower.
Okay, hold on.
Yes, and minus.
Maybe I should be loading your beautiful tensor system in here so that we can actually do this. How do you do it in exact?
That would be x. Let's use Latin letters. Xa p minus b. No, x bracket a, and this is our bracket. Now times p minus b minus x. X minus b, p minus a, and the first one is also an a. It's all lower indices. P minus a. No, the first a in x, it's also a minus. If we want all to be covariant.
Oh, I see. That's your notation for covariant indices.
Exactly. And now x, but it doesn't matter here. We could use all contravariant indices. P minus a.
Yeah. So this is minus a there.
Exactly.
Okay.
The important thing is that this is antisymmetric. So now these A's and B's can be zeros or I's and J's.
I want to get rid of this because I'm confused by it.
Yeah, I think it's better. So now, these A's and B's are the 4-dimensional indices, and we will replace them by zeros or I's and J's, which are the 3-dimensional indices.
Yes.
Okay. So now, let's change A and B by A's and J's. By I's and J's, sorry.
Well, here, but I mean, what I'm basically doing here is I'm making a table with x being, with A goes from 0 to 3 and B goes from 0 to 3. Is that right?
Correctly. Yep.
And then I want to maybe make that in matrix form.
Yes, that's great.
So this is antisymmetric, so it'll have zeros on the leading diagonal, and then it'll have various other relationships here.
Exactly. So what we are saying is that the first column and the first row form what Jonathan was calling the mass.
Moment of mass.
Moment of mass, exactly. And we see there that it contains the x1, x2, x3 multiplied by p0, which is an energy, and then x0, which is time.
Yes. So wait a minute. I'm just to make all the connections here. So this block matrix is the angular momentum tensor, and in 3 dimensions, because we're dealing with 3 dimensions here, this thing here, this little cluster of 3 things, which is antisymmetric with this cluster here, that's the vector. That's what we identify as the angular momentum vector in 3D.
Exactly.
So, for example, just for the hell of it, let me just do something here. Let's how do I make these things all subscripted? I just want to look at the 4-dimensional analog of this. Well, actually, this is 5-dimensional. I mean, 4 plus 1 dimensional analog.
Mm-hmm.
So in the 4 plus 1 dimensional analog, we no longer have, there are 6 components here, not 4 components. So this is no longer a vector. Right? It actually has to be represented as a rank 2 antisymmetric tensor. Okay, but the moment of mass, which is what you're talking about here, go on with the description of that.
Right. So imagine that we have a particle moving in a straight line in which x1 and x2 and x3 are increasing with time.
Yes.
Right. So this is done in a way in which when you subtract P1, P2, and P3 multiplied by time, it gives something constant. It's some sort of initial position.
I see. So you're saying that position times time, which is a kind of a weird object.
No, position times energy.
Where's
if
the
you
energy?
want, imagine that you take those 3
Oh,
objects.
I'm sorry. Those are. Let me actually write this properly. So let's take in line 57 here. Let's take this thing and let's say slash dot, and then let's write out the things. So P0 is otherwise known as energy. I'm not going to write just capital E because it's going to get everything confused. And X0 is time. Okay.
Yes. So now imagine that you divide the whole thing by E.
Yes.
So now you would get X1 minus times P1 divided by E, which is some sort of velocity. So you get X1 minus velocity 1 times time. So that's exactly the initial position of X1.
I see.
And that's why this is a constant. It's a constant because it's, of course, in a straight line, the initial position was conserved.
Okay. Wait a minute. A constant for a particle going in inertial motion.
Exactly.
So your claim is that an inertial frame.
So my claim is that when you talk about J mu nu saying it's a constant, it contains 3 numbers being spin, or if you want, the angular momentum, and the 3 other numbers are the initial position of the trajectory.
Okay.
And that's the interpretation of this moment of mass.
Jonathan, how does that relate to, I mean, the initial position of the trajectory is a different story from what we had just worked out in terms of mass.
I don't know. I don't know if it's a different story.
Okay, all right. So there's some slight mysteries here, but I want to skip ahead because I want to talk about quantization of spin.
Mm-hmm. Can I proffer an initial suggestion?
Yes.
Okay, so in a standard space-time causal graph, right? Spin is as continuous. Angular momentum is as continuous as anything can be in a discrete system because it's defined at the level of individual causal edges,
Wait a minute. So you're saying at the level of a multi-way causal graph?
No, in an ordinary space-time causal graph, as we've been talking about here, right? Angular momentum is as close to being continuous as it can be because it's defined at the level of individual causal edges.
Yes. I mean, what you're saying is in the limit of a large graph. Okay, so the claim is in the limit of a large
the closest thing we can have. Yeah, the closest thing we can have to a continuous quantity in our model, right, is something that's defined at the level of individual hyperedges or individual causal edges.
Right. Large space-time hypergraph, angular momentum will be continuous.
Right. But
I agree.
Here's the point. So this construction that I've described in terms of defining defining these time-like hypersurfaces and then sweeping them around, you can equally well do in the multi-way causal graph, because you can also define time-like vectors and hence time-like hypersurfaces in the multi-way causal graph.
Yes.
So then what you'll and then you'll have this total minus net causal edge flux, where you have causal edge flux not just at the level of individual evolution branches, but actually multiple evolution branches. So each one is going to be a continuous quantity. But here's the thing: if you have causal invariance, then the edge structure is the same between different multi-way branches. So the contribution of each multi-way branch is identical. So at the level of the actual multi-way causal graph, the angular momentum will appear to be quantized at the level of individual multi-way branches, if that makes sense.
Let me walk through that. That sounds potentially very clever, but let me walk through it. Okay, so your first claim is that the multi-way causal graph can have a deformation of angular momentum that also goes across branchial space.
Yes. So what you have to have, instead of just a pure space-like vector, you have to have a combined space-like and branch-like vector. And whether it's possible to express that in terms of the Pauli-Libansky vector is an interesting question.
Well, I think it's more interesting question would be how it relates to twistor space.
I agree. Also interesting. I do not know.
Right, but I mean, so the definition of I mean, that probably, yeah, okay, all right. So in the multi-way causal graph, can define a multi-way angular momentum, just like we can define multi-way energy and so on. The multi-way angular momentum that is defined by essentially GD6 that also go in the branchial direction.
Right. Right.
Okay.
Right. Okay.
Right.
So now imagine that your multi-way system is causal invariant or very close to causal invariant. So the edge, so if you look at each bundle of causal edges in the multi-way causal graph, the edge structure is the same. Right.
Yep.
And in particular, any quantities you compute in terms of numbers of edges or fluxes of edges will be the same.
Yep.
So your multi-way angular momentum will be some integer multiple of a classical angular momentum of an individual multi-way evolution branch.
Well, hold on a second. You're saying in the multi-way causal graph, in the case of causal invariance, the multi-way causal graph decomposes into essentially a product of a union of individual individual causal graphs.
Right, which all have the same edge structure.
Yes, and which therefore all have the same angular momentum.
Right. So now your multi-way angular momentum will be some integer multiple of that quantity.
Well, by integer, we mean very, very large integer of order psi.
Do we?
Well, I'm not sure because I think they might subtract off and things, but I don't know.
No, because we're talking about something that's branch-like local, right? We're sweeping out this plane in the multi-way causal graph. We're not summing over all the evolution branches. We're just summing over all the evolution branches that happen to intersect that hypersurface.
Yeah, okay, all right. So you're making a local probe in the multi-way causal graph to get this local angular momentum, local in both multi-way space, branchial space, and physical space.
Right. So it's not sampling all of the multi-way branches. It's only sampling a local subset of the multi-way branches. And so you therefore will get quantization at the level of the number of multi-way branches.
Why? That's in the multi-way angular momentum.
Mhm.
Okay, so your claim is every branch is
if you had,
identical.
yes, if you had a really strongly causal invariant system, so there was just one multi-way branch, then your angular momentum would always be 1 or 0.
Why?
Right.
Yeah, well, multiples of what? Why?
Well, because either your time-like hypersurface intersects with this multi-way branch or it doesn't.
So you mean when you measure? I'm confused by that claim. So you're saying if I look at the local piece of the multi-way causal graph,
Mhm.
that
Each bundle of the causal edges corresponding to a multi-way branch carries the same angular momentum.
I understand that point.
Yes,
Yeah.
right. So if you just had a single branch, then in units of that angular momentum, the possible values of angular momentum are either 0 or 1.
Fine. But
Right.
but in general, well, you're going to make the claim, I suppose, that whatever leads to the commutator, the XP commutator being H bar. The question is, why is the unit of, you're going to claim that the essentially go ahead.
The natural unit of distances in branchial space is H bar.
And why is this giving us a measure in, you're saying it's giving us a measure in branchial space because that's determining, I see. Your statement is we're looking at a small region of branchial space
Mhm.
to compute the local multi-way angular momentum. We look at a small region in branchial space.
Right.
And the volume of that region in branchial space is measured in units of H bar.
Right.
And why? And you're trying to make the claim that you have, which I'm not yet believing, that you have a somehow you have to have an integer number of or a quantized number of copies of the causal graph in that are within whatever region of branchial space you're looking at. Is that
Right.
the claim?
Right.
So let's look at it a different way. So we got an electron, it's tooling along, and the electron is moving along in space-time. But you're saying the electron also has some extent in branchial space.
Right.
And your claim is that the extent in branchial space defines that there's activity happening both in physical space and in branchial space. And that we can think of the angular momentum of the electron, or the helicity of the electron, so to speak, of its angular momentum projected along its momentum direction. We can think of that helicity as associated with the small bundle of edges in the multi-way causal graph that are sort of within, that are part of the sort of measurement bucket or something that we're using to measure what counts as the spin of the electron.
Right. It's acting effectively as a multiplier to the classical angular momentum, an integer multiplier to the classical angular momentum.
Well, you're saying that the classical angular momentum, you're saying that the point is that an electron has an extent in branchial space as well as an extent, I mean, it has some minuscule extent in physical space, but it has a more substantial extent in branchial space.
Right. And each copy of itself in branchial space has the potential to contribute to its angular momentum by increasing its some multiplicity.
Well, so you're claiming that your average, but I mean, the fact is an actual electron has a half H bar plus minus a half H bar of spin.
Mm-hmm.
So you're claiming that a particle like an electron is localized both in physical space and in branchial space.
Right.
That is an interesting claim and not an unreasonable claim. So I mean, your main claim here is ultimately that particles are localized not only in physical space, but also in Branchial space. Now, how does that relate to wave-particle duality? Because the extent in Branchial space, I mean, the whole idea is that the extent in Branchial space is kind of the wave-like feature of the particle.
Right, but the point is when you measure multi-way angular momentum, your computation is itself localized in Branchial space.
Yeah, so what?
So it's not necessarily the case that the particle is localized in Branchial space. It's only that the parts of it that you can measure are localized in Branchial space. Whenever you perform a measurement of its spin, what you're computing.
It's like you're measuring
space.
the momentum or you're measuring the position. Okay, let's talk about the spin uncertainty principles. I mean, so whenever you're measuring, if you're measuring the position, your detector is at a particular place in space.
Right.
So you're claiming that when you measure the spin, your detector is at a particular place in Branchial space. I'm not totally sure I buy that, but it might be true. Actually, it does seem like it's true, because
if it's not true, then yeah, then you have this problem of your angular momentum multiplied by some factor of psi, and that seems disastrous.
Well, but also think about a quantum computer where you're after all interested in measuring individual spins. You know, one thinks of a quantum computer as having qubits that are localized in Branchial space.
Right. The point is, in order to set up the definition of a spin detector that hasn't decohered is one that's localized in Branchial space. Right. Decoherence is the loss of locality in Branchial space.
Right. So any spin detector must be localized in Branchial space, is the basic claim. Which is otherwise saying that if you've got your quantum computer, which is full of spin detectors, basically, where you need to have a bunch of spin detectors, yeah, you better not have smeared it out in Branchial space. Okay, fine. Okay, now the obvious question here is, okay, great. Okay, so the claim here is that I'm still not completely buying this claim, but let's imagine that.
I'm not saying it's true. It's just, it seems like a natural byproduct of what I already did. So I just thought it was worth mentioning.
Well, okay, but what you're claiming is that the spin would be associated with a limited region of Branchial space, which might contain some number of copies of the multi-way of the causal graph.
Yes.
Okay, so the next obvious question is, let's talk about fermions.
Right.
So let's talk about the relationship between that interpretation and the story of SO3.
Well, yeah, this is the thing. So I don't. Once I have a better idea of how we get things like SO3 or SON manifesting in these systems, then I can start. I might start to have ideas about how spin n kind of arises and how universal covering spaces might work and stuff like that. But obviously, until we know that, I don't think I have anything sensible to say about fermions.
Right, but I mean, in general, the way that we think look, rotational invariance, for example, in our model is, what is rotational invariance? Rotational invariance is statistically, so rotational, okay, what we're defining here with these P forms and so on is, I mean, what we're defining is a bunch of Cartesian vectors, Cartesian tensors, so to speak, or the analog of Cartesian tensors. Okay, next question, my general knowledge question. So if I have a P form, that's like an antisymmetrized Cartesian tensor, right? What is the analog of a spherical tensor in exterior calculus? Because that's what I need to get rotational invariance. I need to have something where the only tensor that survives, the only spherical tensor that survives, is the simplest spherical tensor. I think that would be a Jose question. Does Jose know the answer to that? I vaguely remember that there is an analog of the spherical tensors in exterior calculus.
Well, let's see. So I'm not sure exactly what you mean by a spherical tensor. So the result is that P-forms are like generalizations of geometric objects, right? So a one form will be a line, a two form is a plane, three form a volume, etc. And these things, when subjected to a rotation, they rotate. They are never invariant. They always change. A line into a different line, etc. So there is no P form that stays invariant under rotations other than a zero form, a number.
I understand, but my recollection is that there's an analog of this. Let me look it up.
By spherical tensor, do you mean spherical? You mean like a tensor operator in spherical basis?
Yeah, I think so. I mean, let me look at this. I remember I worked on this once, long ago.
So there is another result, which is the only tensors that stay invariant under rotations are the deltas, which are not deformed, they are symmetric.
Yeah, I remember this. Okay, all right. Let's see if I remember what I'm talking about here. This is actually, you know, I wonder if I looked at vorticity in these. That would be fun. That is deeply suspicious that I had a capital Xi back then for something completely different. Let's take a look. Yeah, here we go. This is what I'm talking about. Tensors that are invariant under all rotations and reflections can have only one independent component. Okay.
Right. So this is the delta result. The isotropic tensors, exactly.
Right.
So effectively, this singles out the combinations of multiplications of deltas, symmetric, they must be symmetric, and the epsilon tensors. Those are the only ones that structurally stay the same.
Okay. But so then the question is, if we are defining a P form using P GD6, what is the statement that, what's the statement of rotational invariance in terms of GD6?
Probably more than invariance, the requirement is covariance. The requirement that under a rotation, they must behave as we said before. Each of the indices gets contracted with a rotational matrix.
Fine, but I mean to say, look, there's an almost trivial statement that if you have a geodesic ball, let's see, what is the right way to say it? I mean, there are a whole bunch of ways to say it that will all be equivalent, that are talking about rotational invariance of that essentially space-time, which is, I think, an easier concept. Okay, but the question is, what we're trying to understand is, well, a couple of questions. First of all, SON invariance, and then for bonus points, SON for n not an integer. Right, now there's this recent work on these Deligne categories and things that claims to be some generalization of SON invariance for n not an integer. I have not understood this. Did either of you, Jonathan, did you understand that at all?
I read a bunch of stuff about Deligne categories, and I mean, I learned some stuff about Deligne categories, but I still don't know this SON for fractional n story.
Okay. Because that's part of what we need to understand. If we want to understand how, I mean, you're basically claiming, okay, let me just tell you my guess about the quantization of spin, which might be wrong. My guess is that it's more related to some kind of topological property along the lines of there are, you know, if you have a non-zero circulation around a point, it is not contractible to a point. Right? It has right, I mean, that's the standard sort of homotopy story. That any net circulation you have, you either have it or you don't have it. It's either, you know, continuously deformable, or there's something left over that's a sort of a discrete topological thing that you can't deform to a, you know, you can't deform away. And again, let me see. Look, I have to admit that the scale of spin is much more something that you would expect to be associated with branchial space. And I had not, I mean, I kind of wonder whether a combination of these ideas, and it's getting hard to think about because it involves topology in this mixture of space and branchial space, might actually be what's going on. And I have no idea what the topology, I mean, we're having a hard enough time with topology in these hypergraphs where we're dealing with fractional dimensional space, let alone branchial plus spatial structure.
Right.
But I mean, coming back to, let's just come back to fermions for a second. So I mean, the big question there is, why should it be the case that, you know, we have, okay, let's talk about charge conjugation for a second, because that's the, or, you know, well, okay, I'm trying to understand, gosh, do we have any idea if we've got a particle tooling along, this is going to relate to charge here. Okay, CPT invariance in quantum field theory, invariance under the combination of charge conjugation, parity, space inversion, and time reversal. Charge conjugation is otherwise known as complex conjugate of the wave function. Do we understand why we might have something like that, or how that might work? What is, okay, time reversal, we kind of understand what that is, I would think, in our models. You just reverse the edges in the causal graph.
Mm-hmm. Right. And charge conjugation is flipping of the branchial, of the multi-way evolution graph.
Okay, that is an interesting claim. Let's see. So let's talk about CPT invariance. So
Because, sorry, go on.
T is reverse the arrows in the causal graph. Okay, now P, parity, is, I guess that could be done by reversing the arrows in the spatial hypergraph.
Right.
Oh, that's cool. That is very cool. Reverse the hyperedges in the spatial hypergraph.
Mm-hmm.
That is cool. Okay, now you're going to tell me.
Well, okay. If you want consistency, C is reverse the branch-like causal arrows in the multi-way causal graph.
Yes.
Because as we know, or we think we know, the natural distance metric in the multi-way causal graph has positive imaginary numbers for branch-like separation, right?
So your claim is,
so well, if you take the complex conjugate, what you're doing is you're making all the i's turn to minus i's.
Okay, so wait a minute. Reverse the edges in either the, is it the multi-way causal graph or is it just the multi-way graph?
It's the multi-way causal graph, I think.
Well, reverse branchial edges is basically what you're saying.
Right.
Wow. If that's right, that's pretty cool.
Well, it's correct if our interpretation of what a wave function is correct.
Yeah, okay. So then the question is, why is the overall theory invariant under CPT transformations? And why is that equivalent? Because in standard quantum field theory, you know, one of the big results is, you know, that the CPT theorem follows from analytic continuation of Lorentz invariance. Right. This is the ultimate sort of, right, the standard CPT theorem just follows by taking Lorentz invariance and continuing, you know, the Lorentz group out of the sort of proper orthogonous setup.
Right.
So how does that work here? So what we're saying then is, oh, I see. Yeah, I think it works exactly the same. Well, at least
it's multi-way causal invariance.
What?
It's multi-way invariance, right?
Why?
We're extending causal invariance to apply to foliations of the multi-way evolution graph.
Oh, I see. You're saying, what you're saying is, oh my gosh, that's really interesting. I mean, so normally we have inertial frames in, you know, normal Lorentz transformations represent transformations of the inertial frames in space-time, right? P and T would correspond to the extreme transformation of the inertial frame in which you are not just, going up to the speed of light, but you're flipping around and flipping the time direction opposite, to the opposite time direction.
Right,
Okay?
right.
Okay, now we have not thought about reference frames in Branchial space that are like the inertial frames of, but what you're saying is,
well, we sort of
imagine an inertial frame that is essentially a flat frame across not only space-time, but also Branchial space.
Right, I mean, that's our minimal model of a non-interacting observer.
Right. Right. Is parallel, is that the reference frames are simply parallel planes in Branchial space, parallel, generated by time, so to speak. Okay. So this is saying CPT invariance. Well, that's really interesting. CPT invariance, at least in the non-interacting case, well, CPT invariance is therefore the generalization. Well, okay, so there's a generalized, okay, first of all, there's generalized Lorentz invariance. Including Branchial rotation, basically. Right, that's what we're saying, is that in addition to rotations in space-time, we've also got Branchial rotation. So what does that look like? The metric there is a combination of your favorite Fubini-Studi metric with some kind of Minkowski metric. Is that right?
Yes, right. I think I call it the multi-way Minkowski norm.
Oh, so you've written this down. Okay.
Yep.
Okay. So what is the multi-way Minkowski norm? Should we pull up your paper? Is it in your paper?
Yeah. We can do. It's in the quantum mechanics paper. I mean, it's kind of what you'd imagine it to be. It's where is it? Let me see if I can find it. Page 33.
Wait a minute. So this is, oh, you're not using that lovely notation of mine with a B for Branchial distance.
I can start doing that. I'm sorry.
I think I would do that. It's a lot clearer than having an X and a Y.
Yeah.
Especially with that ridiculous symbol that I was having a hard time typesetting with a greater than sign on top of or the less than sign on top of the B to indicate Branchialism rather than these. I don't know whether Jose has seen this. This was my little crazy little hack. So with a vector, you do a standard kind of overscript, right? Where you have a like a vector like that, right?
Right.
And so the idea was in Branchial space, to represent a vector in Branchial space, you would do that.
I see.
Okay, anyway, that's just notational hack. All right, but so let's look at this norm here. So you're saying that, okay, so these are various pieces of the light cone, the entanglement cone and the light cone, right?
Right. But crucially, there isn't mutual exclusivity here, right? So you can have pairs of events that are both space-like and branch-like separated at the same time.
Right. What is the analog? What is the shape? So a cone is the shape that represents one of these. What is the joint light cone and entanglement cone? What is that shape? Is it still a cone? Just in higher dimensional space, or is it something different?
It feels like it's not a cone. It feels like it's a cone with cones at every point on its surface.
Yeah, a coned cone.
Right.
What the heck is a coned cone? Yeah, we're not sure what that is. Okay, but anyway, so what we've got then is So I'm still trying to understand this generalized Lorentz invariance. Okay, what is branchial rotation? What is the interpretation of branchial rotation?
Transformation of observer, continuous transformation of observer.
Right, but does that have a standard physical interpretation? So, for example, on a spin chain, for example, what that means is you're sampling more of the spin chain. You know, you're I don't know, that's a very useful way to think about it, but I mean, you're progressively sampling more quantum degrees of freedom. That's what it means.
Right.
So what is the situation in which you're progressively, shoveling in more quantum degrees of freedom? Because usually you're very keen to see only a particular set of quantum degrees of freedom.
Right. You're trying to form this flat foliation
With a certain superposition. But what this is saying is something where you're gradually increasing the number of quantum states that are, quantum eigenstates that are in the superposition.
Right. It's like you're decohering preferentially in a particular direction in branchial space.
Okay, what's the interpretation of that? So imagine you have a spin chain, for example, line of spins. I mean, what that's doing is it's saying you're progressively entangling more and more of that line of spins. Is that right? Or is it that you're moving down the line of spins and forgetting the previous degrees of freedom? Because that's what you'd be doing in space-time. You're moving to a particular point in space, and then you've left the previous point that you were at.
Right, but is this this spin chain you're thinking of, is it a chain in time or a chain in branches? Sorry, is it a chain in space or a chain in branches?
No, I'm saying that it's I'm saying it's quantum degrees of freedom. Whether those quantum degrees of freedom happen to be laid out in space or not is irrelevant to this story, I think.
I don't think it is. Because if it is an ordinary spin chain, as I understand, I don't know much about these things, is laid out in space.
Sure.
Right? So
that is correct.
If it's laid out in space, then when you tip your reference frame in branchial space, you're sampling more of the degrees of freedom and remembering them, because that space-like surface is contained in your foliation. If they're separated in branches, then you're forgetting them.
Right. So it's as if you're just entangling more and more of the spin chain.
Yes.
Which I don't know of an easy interpretation of that. I mean, as you say, it's a little bit like decoherence, but it isn't quite that, is it?
Right. It's some kind of directed decoherence in a way that I don't understand.
All right, but so that's what a branchial rotation would be like. So we don't really have an understanding of we don't have a current interpretation of a branchial rotation. But what we're claiming here is that CPT theorem has to be associated with with an invariance of our system under an extreme version. So under flipping, that is really funky, really funky.
But it explains if it's true, it explains the conjugation of the wave function idea.
What do you mean? The reversing branchial edges corresponds to, so okay.
Because
your branchial edges correspond to antiparticles. Do we understand that?
No. Well, I don't.
Well, but let's just understand. I mean, the claim would be that CPT together are an invariance.
Oh, wait. Maybe we do understand it.
You're going to talk about branch pairs somehow.
Yes, exactly. If branch pairs are the analog of virtual particle creation, or pair production, then reversing of branchial edges reverses the identity of the two elements of the branch pairs.
Does it? I mean, so we have a branch pair. What's a typical branch pair that we can get? We could just do what's a good multi-way system?
I don't know. A goes to B, A goes to C.
Okay. A goes to B, A goes to C. Okay, and what do you want me to draw here? You want me to draw the
Wait, no, you need A1 or something.
Okay, but I mean, we want to draw what? We want to draw the multi-way graph.
Well, let's start by drawing the states graph just so we see what we're doing. But we actually want to draw the Branchial graph.
Okay.
Right. Okay. Now draw the Branchial graph.
Which is just going to be B goes to C.
Right.
Oh gosh.
So you see my point, right? If you reverse the edges, okay. Imagine this were directed in some way, which it would be in the multi-way causal graph because there's directionality of causal connection. Then if you reverse this edge,
I get it.
B becomes C, C becomes B.
Well, that's very interesting. Okay, let's go back to whether we can understand invariance under why there is combined invariance. So that combined invariance, I would claim, is really a transformation on the multi-way causal graph, probably. That all three of these are somehow being applied to the multi-way causal graph. So let's see what they would mean for the multi-way causal graph.
Well, so T and C in the multi-way causal graph just basically means you're reversing all of the edges.
What about P? Because isn't P a space-like edge?
Yes, yeah, it is. That's what I'm saying. So if you just consider T, I think T and C are easy, right? Because that's just reversing everything in the multi-way causal graph, right?
No, but I claim that there are space-like edges here.
In P?
Well, P corresponds to the reversal of space-like edges, but my point is that there are space-like edges, there's space-like separation in the multi-way causal graph.
Separation, but not edges.
True.
All edges are time-like.
Okay, but then we've only got one thing to reverse. So your claim is that the multi-way, okay. So
well, I don't know what my claim is. All I'm saying is, if this is correct, then what has to happen somehow is if you reverse everything you reverse direction of all the edges in the causal graph, and then you somehow invert your hypergraphs, the system you end up with has to be observationally the same.
Right. So hold on. But that has to be the case. I mean, the usual way the CPT theorem is established is by thinking about various analyticity properties of field operators and so on. So what on earth is the analog of that here? I don't know. I suspect it's some continuity property, some property of the fact that there is a continuous limit of the multi-way causal graph. Anyway, I think this is establishable. I'm actually rather, I had not realized that there was such simple interpretations of CPT in our context.
It's cool, right?
It's very cool, very, very cool. And of course, the violation of, I mean, then we know that in physical universe, P and, each, everything except, well, CPT invariance is only, I mean, I don't know, okay, what do we know about the validity of CPT invariance? That might also give us a clue. So what does CPT invariance say? It says, for example, that the lifetimes of particles and antiparticles are equal, although to know that their partial branching ratios to different final states are equal requires CP invariance and isn't true. And I think CPT invariance is supposed to be true about gravity. I mean, that's one of the claims, is that gravity is CPT invariant, which is why antiparticles fall, for example.
Right.
But as I remember, there's some violation of CPT invariance that's associated with some general relativity story. Do you remember what that is? Maybe Jose remembers what that story is?
No, I haven't heard of that. I think what I knew is that it's a mixture of locality and relativity. But no, I haven't heard of violations of CPT.
Yes, it requires some analyticity properties, I think, that are the result of commutation relations for field operators, if I remember correctly.
What I think You might be thinking of there's this rather controversial claim that was made back in the early 2000s of CPT violation being implying Lorentz symmetry violation.
Possibly. Or, well, I mean, Lorentz symmetry, after all, in general relativity, you don't have, I mean, you know, it's a more complicated story of general covariance, not simple inertial frames and so on.
Yeah, sure.
I remember, yes, you're right. I'm remembering some claim related to that it required that the CPT theorem requires Lorentz invariance, which isn't strictly true in general relativity, but I don't remember what actually came out of that. I'm just trying to get some sense.
All I remember is a lot of controversy from trying to track down that claim.
Fair enough. But I mean, that might give us some clue about whether we expect, in what limit we might think that the CPT theorem will be true for the multi-way causal graph, for example.
Right.
All right. We'll take one run for just a couple of minutes on spinors and spin half particles, and then we should wrap this up. So I mean, the question is, in this potential representation of angular momentum, as yet unproven, but you know, the claim of multiple pieces. So what do we think a spinor, you know, the main feature of a spinor is that you don't get back to where you started from until you've gone through a 720-degree rotation.
Right. Which we also know happens in expanding branchial graphs.
Well, have we seen that explicitly?
I think so. Didn't we try to compute? There was some point, I'm vaguely recalling, there was a point where we tried to compute a bunch of dispersion angles, and we were confused when the angles ended up being much larger than we thought they should be.
Yes, that I remember, but they ended up being arbitrarily large, not just a factor of 2.
Yes, but I'm wondering if the factor of 2 thing is telling us something about the rate of branch pair divergence.
Well, I'll tell you another possibility. So either the 2 is because there are branch pairs, or the 2 has something to do with the dimensionality of space-time. Actually, so this is a question. If we go beyond 3+1 dimensional space-time, the structure of the angular momentum, you know, the structure of the particle content changes, right? Because we're dealing with a little group of the Poincare group in higher dimensions, which is not the same as in 3 dimensions. In 3 dimensions, we have SO3, we have, you know, the standard collection of particles. Okay, question, what happens? This is a Jose question, probably. Certainly the structure of spinors is different in even in odd dimensional spacetimes, isn't it?
Yes, I think there is a result that there is a periodicity of 8. You have to go up 8 in dimension to get the same type of spinors. But I think the key result with the spinors is that SON is not simply connected. So you need to go to the covering group, which is the spin group, and there is a 2-to-1 relation. Sure, and that's what creates spinors. So with SON, the representations of SON only give you vector representations.
No, but that's true of SO3, that it's not simply connected. But is that true of all the SON groups?
I think so. Yes, you have to always go to the spin N group. Now, SO3 has the special thing of being isomorphic to SU2.
Yeah, right.
That's truly special of SO3.
Right. And SO4 has another, SO4 is like SU2 cross SU2 or something.
Right, S2LC and this type of thing, yes. So those relations are different, but the fundamental fact that you need to go 2-to-1 relations to the spin groups, spin N groups, I think that holds always.
So the non-simply connectedness of the SON, I mean, what is not simply connected? It's the Lie, the space that corresponds to the Lie group is not simply connected.
Right.
And that happens already at the level of the Lie algebra, yes, if I remember correctly?
No, not really. So a Lie group and its cover.
Oh, that's right. That's right. That's right. The Lie algebra still has the simply right. You have to go to the global structure of the Lie group to see that it isn't simply connected. The Lie algebra is still the same.
Everything is simply connected if you linearize it enough.
Yes, right. So at the infinitesimal, for the infinitesimal transformations, there's no SU, right? It's the global structure of the group, which is, okay, so what's the analog of that for us to, I mean, we think we have some idea for space-time. The analog of rotations is, all right, well, maybe we have to leave this for another time. It's, all right. This was good. We figured out a bunch of stuff here. I mean, there's lots of things to clean up, but I think I'm sort of convinced that we've got a reasonable understanding. Well done, Jonathan. I think I agree with your original claims about angular momentum. I'm not yet convinced about the quantization story, but I think that's...
Neither am I. It's just an idea.
Yeah, right. I'm more convinced about my topological thoughts there. But they may in fact be the same at some level. I mean, it may be that what happens is that there's some sense in which there are, you know, in which there's a different families of sort of branchial fluff around that can exist around this sort of this thing, and that those are, that this set of those things are deformable up to some sort of non-simply connectedness issue. Anyway, that's
right.
I'm still pushing my idea that this has to do with as more of a topological fact that there's quantization there, because to have a topological fact means it's very scale independent. Doesn't matter, you know, what the elementary length is and so on. But I'm not sure, and I do think understanding higher dimensional, yeah, we really need to understand this SON for n not an integer, and the CPT thing is really cool.
Right.
All right. Well, we should wrap this up here, and I should say that tomorrow, I'm doing another live stream, very different from this one. We're probably not going to be talking about the CPT theorem, because I'll be doing a Q&A about science and technology for kids at 3:30 Eastern Time tomorrow. And if somebody starts asking about the CPT theorem and the proof of the CPT theorem, then it's a dead giveaway that we have somebody other than a kid asking these questions. The real question, I think, is at what point does this theory of ours get to be clean enough that the whole thing is really well represented by something that we can you know, make a movie which everybody will understand, and people will really, I mean, you know, it's kind of the analog of when you have some, I think one was lucky in the history of quantum mechanics that these sort of semi-mechanical pictures of how atoms work came before the quantum mechanical theoretical description in terms of eigenfunctions and things of how atoms work, because there was sort of already a sort of a good movie level picture to make, and we're perhaps going in slightly the opposite direction. All right. Well, I'm sorry I didn't get to as many of the questions on the live stream here. I hope maybe other people were answering those. Well, thanks, Jonathan. Thanks, Jose, and thanks to everybody on the live stream. And we'll see you another time for another. I think we'll. I'm not sure what our next discussion is going to be about. Whether we'll continue, we might try and push forward with this and see whether we can get to charge and local gauge invariance. Okay, thanks, and goodbye for now.